68. Optimize water distribution in a village. So there are n houses in a village. We want to supply water for all the houses by building wells and laying pipes. Let me make a drawing of the meaning of the problem. So I'm not gonna explain these areas. I'm not gonna read these areas one by one, but I'm gonna explain what's the meaning of these areas. Normally, I think most of us can understand what is the meaning of the problem. So we are having a graph. So we have the node, we have n node, and the node will be just starting from 1 to 3. So the node is not starting from 0, it is starting from 1. So the node is for the house. And for each of the two houses, maybe other two houses, we have edges. So the pipe is just edges connect to the house. So for example, 1 and 2 connected with a weight. So the weight is 1, this 1 is for the cost. So 2 and 3 have another cost, it is also 1. But we also have wells. So the wells can build inside the house. So for example, we can build some wells inside each of the house. But there is a cost for building the wells. So for example, the cost of building the wells, the first well, so the wells I minus 1, so it means if the node is 1, 1 minus 1, it is 0. So this one, for building a well, the cost is 1, and this is 2, and this is also 2. So the problem becomes whether we're gonna choose well or whether we're gonna choose pipes. But definitely we're gonna choose some wells and some pipes. So for this problem, we are just giving 2 pipes. If there are 3 pipes, definitely we're gonna try to choose the minimum cost. But how can we deal with the wells? If this is a minimum spanning tree problem, normally we just care about the edges. We are not caring about the cost of the wells, because the wells is just a node. It's difficult to calculate by using the minimum spanning tree algorithm. So how can we build a well? Can we build it inside its house and make it connected? So for example, if we build a dummy well, so for example 1 prime and 3 prime, so that is just a dummy well, and here gonna be 2 prime, and then we're gonna use this 1 prime to connect to the house 1, and 3 prime connect to the house 3, and 2 prime connect to the house 2. So if we build the graph like this, so what's gonna happen? Let's just check. So in this example, if we build it like this, we cannot use the minimum spanning tree, because if we want to use the minimum spanning tree, basically we need all the edges. So this is the edge, and this is the edge, and this is another edge, another edge, another edge. This means all the wells we need to use. But we don't need to do that. Maybe we just need to use the sum of the wells. So for wells 1, 2, and 3, 1 prime, 2 prime, and 3 prime, actually we may just choose 1 or 2 of the wells, not all of them. The only case for all of the wells is that maybe for building a well is the cost is very small, maybe 0.1. So we don't need to choose all the edges. We just need to choose the well, 1 prime, 2 prime, and 3 prime. But that is not the case for using the minimum spanning tree, because if we do it like that, we don't need to choose all other edges. So it means if we build a dummy edge directly connected to each of the nodes, we build 3 dummy nodes, it didn't work. If it didn't work, so why not we just build 1 dummy node? So let's just try to build 1 dummy node. Let's see what's gonna happen. So if I just build 1 dummy node, so I'm gonna build a dummy node 0. Because for this graph I don't have 0. So I'm gonna use this dummy node 0 connect to all the other nodes. So what is the meaning of the well? So for this dummy node 0 to 1, it means the first well. So I have a cost of the edge. So it's gonna have a cost of 1. And secondly, with the node 2, I have a cost of 2. And with node 3, I have a cost of 2. Now the problem becomes easier. It becomes the minimum spanning tree problem. So for this problem, if we do not use the adds, we can directly use those blue colored edges. It's gonna still work because all the nodes will be connected. This is only a dummy node, so there's no cost in this dummy node. Similar as other node, there's no cost, but there is edges for the cost for 0 to 1, 0 to 2, and 0 to 3. And the edges is the cost of building the wells. 0 and 1 connected means building the first well. The cost is 1, 0 to 2, it is 2. Yeah. So in this way, we do not need to choose all blue edges. Maybe we're gonna choose some black edges. Maybe we're gonna choose, for example, this is a well. We're gonna choose this edge, one edge, and this is gonna be the second edge. Yeah. Let me try to use another color. Let me use red. Yeah. Maybe we're gonna choose this edge first, and then the second edge, and then the third edge. So what is the cost? The cost is 3. So that is our answer. But for finding the such edges, we can use 2 algorithms. So one is the Kruscal's algorithm, another is Prim. Yeah, another is Prim's algorithm. So I'm gonna use 2 methods to solve the problem. But the difficult part is this one. How can we translate the wells by using a dummy node and connect it to all other node? Yeah, so we need to translate the problem of the wells to the edges. So by translating the problem, we can use a dummy node connected to all other nodes. And this is a typical way of solving the graph problem. Actually, this is the hard way. Normally, we cannot think about it like this. We have to practice a lot, and then maybe, yeah, we can find a dummy node and connect it to all other nodes as the edges of the cost of its wells. Yeah. Now let's go back to the problem. So let's start the coding. So first of all, I'm gonna use the unified first. So for the unified, basically we can choose Kruscal's or Prim's. If we choose Kruscal's algorithm, basically it is the sort plus the unified. So because we are going to use a unified, normally I'm gonna copy the template of the unified and then start to use it. Yeah, because for our problem, it's not about talking about unified. Basically, it's about talking about the minimum spanning tree. So I prepared the graph. I have the find union and it's connected. It's connected is just for checking if 2 nodes are connected or not. Now I'm gonna prepare the dummy node with the edges. Yeah. So I'm gonna prepare the dummy node with edges. So for I in raise 1 to n plus 1. So this means the node 1, 2, and 3. Yeah. So the pipes should append the edges. Yeah, because I will have more edges. So the edges will be 0 connected to I and with a cost. So the cost will be the wells I minus 1, because this is according to the description, the wells I minus 1. If I node is 1, it's going to be the wells 0. It's going to be the first one. So my I is 1 to n and wells I minus 1. So this means all the well will be connected to each of the node. It means I translated these wells to the edges, and I put the edges inside a pipes array. Now I can start using the unified. So pipes can directly sort it. So I'm going to use a lambda function to sort because it's going to be the third index. So x and x2. Now my pipes has already been sorted. I can directly start the unified. So I'm going to prepare UF with the result. Unified with nodes would be n plus 1 because I prepared a dummy node 0. So it means from 0 to this means n equal to 3. I have 3 nodes, but I have one more node 0. So it's going to be n plus 1. And the result would be starting from 0. Now I'm gonna check all the edges. So for UV and cost C inside the pipes. Yeah. If not, UF dot is connected. So if U and V is not connected, I'm gonna connect it by using the union. I'm gonna connect the U and V, and the result would plus equal to the cost. Finally, I'm gonna return the result. The time complexity for the Kruscal's algorithm is n log n. because the main part is coming from the pipe's sort. N is the length of the pipes. So the length of the pipes would be, the length of the pipes is 10 to the power of 4. If we use a dummy node connect all other nodes, it is still to the scale of 10 to the power of 4, so it is n log n. So n is 10 to the power of 4, so it should work. Now let me run it to check. As you can see, it works. Now let me submit it to check if it can pass all the testing cases. Yeah, as you can see, it's pretty fast and it passed all the testing cases. Now let's try to use another method. It's gonna be the Prim's algorithm. Yeah, I didn't make a drawing of what is the Kruscal and what is primes, but let me make it simple. So yeah, for the Kruscal algorithm is that we're gonna use the sort plus unified. So for sort, we're gonna sort the pipes directly. For finding the edge, for the Kruscal algorithm, we just start from we just start from any edge. For example, we're gonna start from the shortest edge first because we sorted the pipes. We're gonna start from the shortest edge, and then we're gonna choose the longer one. Yeah, because the edge is in ascending order, and then we're gonna choose next, maybe longer. Yeah. Next, we're gonna try to connect them also according to the sorting. So the pipes are gonna be sorted. It's gonna be connected maybe like this, and this is gonna be our final result. So this is for the Kruscal algorithm. But what is the Prim's algorithm? Prim's algorithm is basically we're gonna use a priority queue, and we're gonna use a weighted set. We're gonna explore the node one by one. First of all, we're gonna choose a random node because for our problem or for other problem, we don't know how many nodes, but definitely we're gonna have a node 0. So we're gonna start from node 0 because for our problem, we prepared a dummy node. There is a 0 inside, so we're gonna start from the smallest node. So it's gonna be 0, and then we're gonna put the 0 inside our weighted set. So it means we're gonna explore from this 0. So we're gonna explore from this 0 node first. Yeah. And then we're gonna choose some edges, and we're gonna choose the shortest edge. Maybe this one is the shortest. Maybe this is 2, and this is 3, and this is 1. So we're gonna choose the shortest. If we choose the shortest, we're gonna choose this edge with the cost of 1. Maybe it's gonna connect it to 1. And then from 1, there are gonna be many edges. We're gonna choose the shortest. Maybe this is 3. Yeah. And then we're gonna put 1 and put 3 inside the weighted set, and we're gonna start to explore more and more until we find the answer. Maybe this is 4, and maybe this is 2. We find the answer. Yeah. So we will ignore all other edges. So this is for the Prim's algorithm. Prim's algorithm, basically we're gonna use a priority queue, and we're gonna use a weighted set to sort it. If we already find an edge, so we're gonna put it inside the weighted set, and then we put 3, put 4 inside the weighted set, and put 2 inside the weighted set, and finally we find the answer. Because if we wanted to explore 0, we cannot do that because it has already inside the weighted set. Yeah. Now let's try to use the Prim's algorithm to solve the problems. So similarly, we're gonna prepare an adjacency list. But let's just define an adjacency list. Default dict with a list. Yeah, because we already have the pipes. Let's prepare the pipes first. So for UV and C inside the pipes, we're gonna prepare as GU dot append with V and cost, and similarly, because it is undirected, yeah, we're gonna append the V with cost. So this is the first step. Now we are going to prepare the dummy node because we already have the dummy node. So for the dummy node is for I in range from 1 to n plus 1. Because we're gonna use the 0 to connect 1, 2, and 3 in this example. So it's gonna be G0 dot append. Yeah, as you can see that if you think about the dummy node, normally for building the graph, it's going to be easy. So inside it's gonna be the I with the values. Inside it's gonna be I minus 1. And similarly, it's undirected. So the I should append with 0 inside and values I minus 1. So after that, we've already built in the adjacency list. Now we just need to prepare the priority queue. So for the priority queue, we're gonna prepare a PQ and a result and a visited set. So the PQ inside should have 2 values. The cost gonna be starting from 0 because for the first node we are starting just from 0, and the first node gonna be 0 because I prepared a dummy node 0. And the result would be 0, and the visited set would be an empty set. Now we can check the priority queue, and we're gonna pop it out the cost and the node. So Cx would be equal to the hit pop of the priority queue. After popping, so we're gonna check if this node is inside the visited set or not. So if x not inside the visited set, we're gonna explore more node. Yeah. So we're gonna put it inside the visited set, and we're gonna plus the cost. So result would plus the cost. Then we're gonna explore. So the Prim's algorithm is basically an explore algorithm. We're gonna explore one by one until we find all the results. So how can we explore? If it is not visited, we're gonna explore. If it is inside the visited, we will do nothing. Yeah. So there are 2 steps. Basically, we're gonna put it inside the visited set and explore. Put it inside the visited set and explore. So now we are going to explore. So for y and cost, because the adjacency list is the first is the node and then the cost. So for y and cost inside the dx, yeah. So no matter how to explore, basically for this one, we have to check if it is inside the visited set or not. So if y not in visited set, so we're gonna put it inside. Yeah. So we're gonna put it inside. We're gonna use a heap push with PQ and a tuple of y and cost. Finally, we just need to return the result. So for here, you cannot use a visited. You cannot put the y if y not in visited set. Visited set should not put a y inside, because here we are still exploring more nodes. If it is not inside visited set, we're gonna still visit it. If you put it inside, normally for here, maybe you're gonna miss some other node. So for here, we just need to put it inside the visited set. We don't need to put it. We just need to put it inside the priority queue, but we don't need to put it inside the visited set yet, because we need to explore. We're gonna try more and more. If we already tried this one, we're gonna put it inside the visited set. So you need to take care about the algorithm, about at which place we're gonna put it inside the visited set. Now let me run it to check. There's something wrong. So the first example is okay, and the second example is wrong. One, two, and one. 1, 2, and 2. Yeah, because there are also duplicate pipes. So let me check. Yeah, there may be duplicate pipes, but if we are using the priority queue, it's gonna always be the smallest edges. PQ result and visited set. So while PQ, we're gonna pop it out, and if it is not inside, we're gonna put it inside. y and cost. Yeah, so here is something wrong. I need to put the cost and y, not y and cost, because for here the tuple is for the priority queue. The first index is the cost, and the second index is the node. So it should be the cost and the node. And but here it is the opposite, because inside the adjacency list it should be the node and cost. Now let me try to run it. Now as you can see, it works. Now let's analyze the time complexity. So here is just for building the adjacency list. So for building the adjacency list, basically we just needed to traverse the pipe. So this is the ON, and for here, so this is a priority queue, and this PQ is how many edges, and for each of the PQ there are gonna be the pop and push inside. So the time complexity gonna still be n log n. N is the number of edges. As we know that the time complexity for the Prim's algorithm is the same as the Kruscal's algorithm. So for us, we can try to use one of them, but for most of the time I prefer to use unified. Yeah, because unified is less coding, and sometimes unified should be faster. Yeah, as you can see that unified is the Kruscal's algorithm is much faster. As you can see here is 17.2, but let's check the record of the unified. As you can see that the unified is is faster normally. Yeah, because it's 93%, and here is just 11%. So for most of the time I'm gonna try to use the unified, because unified is easy to write and there's less coding, because the template is not the coding. And thank you for watching. See you next time.